Good afternoon, everyone. My name is Kenneth. I'll be starting our presentation on raising. This is group five, and our topic is raising a holistic service for dealing with memory leaks in production cloud infrastructure. And here with me are my teammates, Shrey, Tejan, and Hani. So I'll be starting over the presentation. This research focuses on one of the biggest reliability challenges in cloud computing, that is memory leaks. These leaks can slowly drain systems, also causing performance drops, crashes, and also expensive VM reboots. To address this, Microsoft and John Hopkins researchers developed Raising, that is an end-to-end system that automatically detects, diagnoses, and also fixes memory leaks in large-scale environments. So it's a lightweight, scalable, and also runs continuously across millions of hosts. And that also reduces memory-related reboots by more than 40 times. So our next slide is the problem. So memory leaks are a very big issue in cloud environments because they slowly drain system memories, causing performance drops, crashes, and also full VM reboots. So in a large platform like Microsoft Azure, these problems can spread very fast. Existing tools either use too much system power, lack accuracy, or just don't scale well in production. Why leaks are hard in clouds. So in the cloud, leaks don't show up right away. They happen slowly, under rare and unpredictable conditions, which also makes them hard to reproduce and also trace. So static tools often miss these hidden leaks, while dynamic tools also take too many resources to run continuously. Now, introducing Raisin, that's where Raisin comes in. So Raisin is a system built by Microsoft and John Hopkins, researchers to automatically detect, diagnose, and also fix memory leaks in production. It's a very lightweight and also runs across millions of Azure hosts, and also uses a smart divide and also conquer approach to handle processes like kernels and also drivers efficiently. Real examples of a leak. Here's a real case from Azure. A developer accidentally used a timeout parameter incorrectly in an API, which caused a kernel memory leak every few seconds. So over time, it filled the system memory and also caused crashes. Raisin was designed to catch exactly this kind of leaks early before they affect performance. So when it comes to the Raisin leak detection process, Raisin collects memory data every minute from all hosts and groups. It synthesizes bucket to also find abnormal growth. It also uses statistical analysis, thereby to identify when a process memory usage, looks very suspicious, and it then goes ahead to flag it for, a closer inspection. And all this without slowing down production systems. We move on to the next slide, and that's the raising diagnosis and mitigation. So once a leak is detected, raising takes a very live memory snapshots to figure out where the problem is coming from. It compares those snapshots to healthy references and also identifies the exact function causing the leak. From there, it can safely restart the process and also reboot the node if needed, and keeping the system running smoothly. The next slide we have here is the impact of Azure. So Raisin has been running in Azure for more than 3 years, and reports over 20 leak cases each month. It also reduced VM reboots due to low memory by 41 times, and also cut allocation errors by tenfold. This shows how effective it's been at improving cloud reliability on a massive scale. And with that, let me hand it over to my colleague, who will walk you through how resilience detection and diagnosis process works in more detail. Thank you.
Hi, my name is Shrey Patel and I will take over from here. So the design of leak detection. So Resin separates leak detection from diagnosis to keep things lightweight and scalable. The main idea here is to catch leak early and accurately without slowing down production. So it uses a two-level detection system, first at a global level where it looks at the pattern across all the Azure machines using bucketization and pivot analysis, and then a local level where it zooms into an individual processes. This separation helps reduce overhead while still giving precise detection at the cloud scale. So there are certain challenges in the detection. Detecting memory leak in a massive noisy cloud environment is a no small feat. Azure workloads constantly fluctuate, creating lot of noise. Leak also slowly grows and sometimes over weeks, making them hard to catch early. And because Azure runs millions of VMs, Resin has to sample memory data only every few minutes and still be accurate. So the algorithm must work with coarse data and still pinpoint slow, subtle leaks with the minimum false alarm. So there is an agent. The name of the agent is Lightweight Monitoring Agent. Here where the magic starts. Resin uses a lightweight monitoring agent installed on every Azure host. It collects detailed metrics, process stats like the private memory working state and a paging file usage plus kernel pool usage from the poolmon tags. All this is aggregated hourly to reduce noise and data load. Think of it as the data collection backbone of Resin silently monitoring millions of machines with the minimal overhead. This is the image where you can see that it is taking the memory data from kernel memory, process memory and attributes. Now, it also has the bucketization based pivot scheme. This is Resin's secret part where it groups memory usage data into the size buckets, say 50 MB to 50 GB, and pivot it by attributing like the process name, services or kernel tags. Then it hosts anomalies by checking if the bucket count exceed a dynamic baseline using the mean plus 3 standard deviation rule. The brilliance here is that individual noise cancels out across the fleet so leaks stand out clearly. This approach slashed detection time from more than a day to an hour across millions of nodes. Here is an image where there is a two part where you can see one is the non-leaky component where there is no leak and another one is the leaky component where you can see an abnormal bucket. Then comes the local process level detection. Once a bucket is flagged, Resin drills down to identify which specific processes are leaking. It builds two Gaussian model, one for absolute memory usage and another for the rate of change. Then it applies a moving suspicious interval algorithm to find where memory leak constantly grows. Finally, it calculates a score based on the growth rate, duration, and a usage level, giving a ranked list of actual leaking process. This helps developers focus on the real culprits, not false alarms. This is the formula where you can see the formula, and this formula gives us the result which balances growth, magnitude, consistency, duration, and absolute level. The detection returns a ranked list of the leaking processes with feeding diagnosis and mitigations with precise target instead of noisy fleet-wide alarms. And from here, my another teammate will take over.
Hello, my name is Tejan Thakkar and I will be presenting next few slides. Now that Resin has identified which processes are leaking, the next step is diagnosis. Detection alone cannot fix the problem. Developers need evidence. Resin performs automated diagnosis by taking live heap snapshots, comparing them with healthy reference hosts, and highlighting the suspicious allocation stacks. responsible for the leak. This makes root cause analysis fast and actionable. To diagnose leaks safely in production, Resin uses Windows Heap Manager and the Performance Recorder to capture lightweight heap snapshots. These snapshots include stack trace IDs, allocation sizes, and allocation counts. They are taken periodically, usually every 30 minutes. So Resin can build a time series of how allocations grow. Importantly, tracing is only enabled temporarily for target process, keeping overhead low. Since taking heap snapshots on every machine is costly, Resin selects only the top candidate for profiling. Hosts are ranked based on severity score, clearness of the leak pattern, and overall activity level. Ideally, Resins choose the top 3 hosts that shows the strongest leak signals and minimal user workload, ensuring both accuracy and safety. When evaluating snapshots, Resin classifies leaks into one of 3 common patterns found in 51 real cases. First is the steady pattern. Memory grows linearly and constantly. Second is stair pattern. Memory grows in step, leaking only when certain events occur. Third is spike pattern. Large and sudden allocation from event driven behavior. Each pattern has its own triggers and timing for when snapshots should be taken, ensuring the system captures meaningful data rather than noise. One of the challenges in diagnosing leaks is that many allocations are normal. To filter this out, Resin maintains a reference database of snapshots from non-leaking hosts with the same fingerprint. By comparing snapshots of leaking hosts against this reference set, Resin removes benign allocation and focuses only on unusual growth. Resin's diagnosis engine uses algorithm 2, which compares two snapshots, the latest snapshot and the previous one, and correlates them with reference snapshot data. It groups allocations by stack ID, identifies newly growing or significantly increasing allocations, remove anything that appears in reference hosts, and then ranks the suspicious stacks. The top ranked stacks are the most likely root cause and are sent to developers as a clean, readable report. Even after leak is diagnosed, deploying a code fix can take days or weeks. To prevent customer impact, raising includes automatic mitigation. The goal is to safely contain the leak without causing downtime. Mitigation starts with the least disruptive action like restarting the process and escalates only when necessary. Thank you so much. Now other person from my team will be presenting next few slides.
Hi everyone, my name is Hani Youssef. In this last part of the presentation, I will talk about how Raisin handles leaks in production, how well it works, and what we can learn from it. This slide shows Raisin's mitigation decision tree, and mitigation here means what action Raisin actually takes to fix or reduce the impact of a leak. After Raisin detects and diagnoses a leak, it does not reboot the machine right away. Instead, it follows a step-by-step approach, starting with the least risky action. First, it tries to restart the leaking process or service. If the leak is in the kernel space, it reloads the driver that is leaking. If these actions do not solve the problem, Raisin does a soft reboot of the host. A full reboot is the last option when nothing else works, as a fourth option. All these actions are controlled by safety allow lists, so Raisin only changes processes and hosts that are approved for automatic actions. Moving to the next slide, we can see here at the cloud scale, Raisin has to manage many hosts at the same time, not just one. In this workflow, Raisin decides where to act first. it gives priority to hosts that report low memory events and are in region that already have high capacity usage. Inside that group, Raisin focuses on largest leaks or the fastest growing leaks first. This way, it handles the most serious problem earlier. Raisin is also aware of ongoing diagnosis. If a host is currently taking heap, snapshot, or collecting traces, Raisin can delay a reboot, or so this data is not lost. When it leak, when the leak signals stop, because the bug is fixed or the host has been cleaned up, Raisin automatically stops mitigation on the host. Also, in the production cloud, we must protect customer workloads while fixing leaks. So, uh, with that being said, Raisin actually treats hosts differently based on whether they are running customers' virtual machines or not. So in the case of an empty host where no customer virtual machine are included, Raisin can reboot immediately once it confirms there is a leak. However, on non-empty hosts, Raisin first moves the virtual machines away to other hosts, and only then it reports the leaking host. This matches common SRE practice. Move the workload first, then repair the machine. After the matrix and logs return to the normal, Raisin turn off mitigation for that host. This prevents repeated reboots and reduce the risk of harming a stable system. For the evaluation part, if you see here on figure 8, we will summarize how Raisin performance is how Raisin performs in real production. As you see in figure 8 here, it shows a number of memory leaks cases that Raisin finds and reports each month. The bar shows how many cases are confirmed, unresolved, or denied. And the purple line, if you see the purple line, it shows how many cases come with traces. The main point in this reason, the main point in that is Raisin keeps finding many real leak cases, and over time, more of these cases include good trace data. This means operators are not just told that a leak exists, that they also get enough information to debug and fix the bug behind the leak. Here are some key metrics in these screenshots. This slide shows several important metrics that describes Raisin impacts and accuracy. Taking an example of figure number 8, number 9, it shows the unexpected virtual machine reports go down a lot after Raisin is deployed. This means fewer virtual machines are crashing because of leaks. And also in figure 10, it shows a drop in virtual machine allocation error rates. So memory leaks are no longer causing many allocation failures. In figure 11, it shows a ticket resolution ratio. Also in figure 14, looks at a specific looks at a specific leaking driver. It shows how many hosts Reason mitigates per day. At first, many hosts need mitigation, then the number goes down as the driver is patched and leak disappears. Figure 15 and 16 show false positive and false negative for different settings of the detection algorithms. The bucket-based settings keep both types of error low, which means Reason is accurate and does not overact to noise. Also in figure 18, it shows the CPU and memory usage during tracing. For two hosts, the lines stay almost flat, which means Reason's tracing and heap snapshot add very little overhead and are safe to run in production. Overall, these metrics shows that these metrics show that Reason reduces failure, helps close more tickets, and does this with a low cost and low risk. Getting to the lessons and the limitations from the results, we wanted to share some lessons and limitation learned from this research. One of the lesson is fleet level signals, like how memory events and error rates are good for spotting leaks early, especially at large scale. Heap snapshot with referencing based ranking help find the real leak route, even when the heap is very large and noisy. Limitations are slow or very small leaks might never cross the chosen threshold, so Reason might miss them. And it is still hard to reduce production leaks in a test lab because test traffic is usually simpler than real customer workloads. So Reason is powerful, but it is not perfect, and it works best for leaks that have a clear and visible impact. Going to the related work, now I will briefly place Reason in the context of other leak detection approaches, static analysis tools, scan sources, static analysis tools, which is a scan sources code to find patterns that may lead to leaks. They are useful, but they often miss leaks that only appears under real runtime condition, such as long uptime or specific traffic pattern. Also, dynamic profiler and leak detectors can be very accurate, but they are expensive to run all the time, especially on millions of processes and hosts. Reason takes a different approach. It works as a service in production. It uses a lightweight monitoring across the fleet. Then only the suspicious hosts, it runs heap snapshots, traces, and mitigation actions. This design makes Reason practical and at the cloud scale, where we cannot attach heavy debugging tools everywhere. Also, to conclude what we just went through, Reason changes memory leak handling from a manual reactive task into a continuous automatic services. It combines bucket size detection across many hosts, heap and traces based diagnosis to find leak route, and safe automated mitigation that respects customer workloads. In production, this loads is fewer leak related reports and location failures. and gives engineers better data to fix the bug behind the leaks. For large cloud provider, this means higher reliability without placing heavy debugger on every machine. Last is the reference and closing of this presentation. This final slide lists the recent research paper that we used as a main reference for this presentation. That brings my section and our full presentation to an end. Thank you so much for listening